All right, well, welcome back, everybody. We're going to wrap it up with this final session. This particular session is on feedstock processing for waste conversion projects. We've got three presenters. Let me just go ahead and introduce all three of them to get us started. So our first presenter is going to be Hartmut Bendfeldt, who's president of E-Factor 3, and I've actually had the opportunity to run a couple of trials with Hartmut with agricultural film mulch. For some of you that may not know, I also run the Agricultural Plastic Recycling Conference, and there is definitely a nexus between this topic and agricultural plastics. And so, Hartmut, hopefully you can share a little bit of what we've done through some of your slides. Hartmut's going to be talking about renewable fuels, ways to do it. Then we've got Rebecca Brown, who's a microbiologist with Idaho National Laboratories, and Rebecca is going to be speaking on MSW decontamination methods to improve biofuel yields. And then finally, Dr. Nepu, is it Saha? Dr. Saha is a postdoctorate research associate, also with Idaho National Laboratories, and is going to be presenting on reprocessing of municipal solid waste towards thermal insulating materials. So let's go ahead and kick it off and let Hartmut talk to us first. Hartmut?
This is the up and down. Okay. Yeah, good morning, everybody. It looks like it's thinned out quite a bit since we're getting to the tail end of this conference, but appreciate you few sticking around for the last couple of presentations. So, just to introduce myself, my name is Hartmut Bendfeldt. I own a company called E-Factor 3, stands for Environmental Engineering and Equipment. So we are a distributor of equipment from single type machines to complete integrated solutions for the processing of waste and plastic streams to fuels or recycled materials. So our business is basically offering waste processing systems from pre-shredding all the way to commodity separation, and plastic recycling systems that include dry cleaning technologies, wet wash systems, extrusion systems. So we can handle a lot of different recyclable materials and waste streams. So one of the things, we've heard a lot about the pyrolysis gasifications, and it looks like that every system has different requirements to the fuel specifications. So one of the things that we like to know as soon as possible in the process is what is actually the source of the waste stream? What is the composition of the waste stream? What's the density? What's the final specification of the fuel? Is there restrictions on paper content? Is there restrictions on PVC? Is there specific polyolefins that you have to get? So the more homogeneous the input material is, the simpler the system becomes. A lot of systems start somehow with primary shredding. Primary shredding, especially when we have agricultural film or mixed film out of MRFs, often contain surprises, common bales. These bales have to be broken up. With the primary shredder, we can easily feed complete bales with wires, and then after a primary shred, we can do mechanical separation. So and these pre-shredders come in different versions. They come in stationary versions as well as mobile versions. So there are certain projects that might require something in the field. We have equipment that can be mobilized, is track mounted, and can be run anywhere in the world. One of the next steps in the process is obviously to remove ferrous metals. That's done with inline magnets. I'm not going to go into deep details of this type of equipment because I'm sure that everybody is fairly familiar with that type of equipment. When it comes to film coming out of the ag industry, we have a lot of fines, inerts, and heavy contaminants in it. So that is typically removed through process of screening and wind sifting. So a screening equipment can remove, again, fine particles that get loosened up to the pre-shredding process. We can also create multiple fractions of sizes if it's desired. That really depends on the downstream separation technology. And with a wind sifting device, we can remove heavy contaminants, and we can also separate rigid and film materials from each other in one step. This is the principle of it. Is there a pointer on it? Is that the top?
Yep.
Doesn't work.
Widescreen pointed towards the screen.
Oh.
Point towards the screen. There you go.
Oh, here we are. So the material is fed in here. We're using air technology in the separation drum. We separate out heavies here. So if it was agricultural plastic, the heavies would come out here and go on to this separation step. And then if we wanted to take off a very light film, we can suck it away. So that gives us a heavy, medium, and a very super light fraction. In some cases, when we're talking about a mix of residual plastic from the MRF, we have typically 1 through 7 materials. And a lot of the pyrolysis do not like certain plastics. They like polyolefins, PEs, PPs, and in some cases PSs. PVC is something that always needs to be removed, and PET is typically also something that's not desired. So we can integrate optical sortation in a system. And then the secondary downsizing is typically done with single shaft shredders, in some cases granulators. The selection really depends on the material that you want to process. So we offer fine shredders in different sizes that go up to 25 tons, 23 tons an hour. This is kind of designed. A lot of single shaft shredders do use the same principle, small square inserts on a rotor. In certain materials, this design with a multi-edge rotor gives us some benefit that we don't get melt of specific LDPE films. So now I'm going to just bring up a couple of examples of materials that we can process in. The wood waste is a fairly simple type material to process. Same with commercial and industrial waste streams. So a simple line like this that's comprised of a pre-shredding equipment, a magnet, a wind sifter, and a secondary shredder can handle up to about 20 tons an hour of clean materials. If we had agricultural film, we would integrate a screen in it as well. Right here, so we pre-shred, magnet, screen, wind sift, and then secondary shred. When it comes to also MSW or MRF residual, there's often the requirement to have a more complex system, including optical sortation, separation of organic fractions. So with these technologies, we can create a fuel, and if it goes in the cement industry, it doesn't have to be cleaned much. But when we come into the recycling, in the chemical process, there's a requirement to clean this material up. Mixed film residuals, mixed rigids, ag plastic. And ag plastic seems to be a very, very interesting commodity for the pyrolysis because it's very hard to recycle material. So in our experience in the projects we are working on, we found out that it has to be fairly clean, small dirt contamination. It has to have a consistent particle size. If it's rigid, it needs to be somewhere in the 3/8 to 1/2 inch particle size. If it's film, there's certain technology that can take the film flake at 1.5 pounds a cubic foot. Others have to densify it. Typically only the polyolefins, the PEs, the PPs, and the PSs. In the end of the day, all of this pre-processing is very similar to the mechanical recycling process. And in many cases, paper contamination have to also be minimized. And that, again, depends on the specification of the actual plant. And for that, we offer some technology that is called dry cleaning. So we have a supplier that's called MAS. It's a manufacturer of a complete dry cleaning process for egg film. That technology on the, somehow I have a hard time with this. This would be a shredded egg film, dirty. This is the dirt residual that we are pulling out. And this is the end product, the clean flake. With that, we take egg film from its 25% moisture and 30% dirt contamination to 1.5 to 2% moisture and less than 0.5% of dirt contamination. It's fine dirt that's embedded in the structure of the film. This is the principle of this technology. It's a batch-fed continuous process. So flakes of material go into this centrifuge from a buffer silo. And the blue represents the plastic, the black represents heavy contaminants like small pieces of metal or glass that we have not captured beforehand. And the greenish particles represent the moisture and the dirt that's in the material. So the unit basically pulls this material into the centrifuge and is holding the material in a turbulent environment inside this machine. And we have heated air going in at about 100 degree F, so it's not really hot, it's warm air. And it dries through this process. It dries off the dirt on the surface of the flake, and then the actual friction among the particles deliberate the dirt into the air, and there is a continuous suction on both sides of this machine. We're taking away the dust-laden, wet air and filter it out. And once we reach a certain stable temperature, we have the material in there for another about 15 seconds, and that cleans the material to a very good degree. Now, this technology cannot remove any oily or greasy substances, so it's not designed for food packaging or things like that nature. This is what a complete system looks like. So we go basically from a buffer silo to the first centrifuge where we do the majority of the work. Then it goes to a second centrifuge where we just rearrange the material to get some extra cleaning. And these units come in two different sizes, and it's always measured in input capacity. So if we're looking at the larger unit at 1,500 kilograms input, 3,300 pounds, you have to deduct probably 50% of what you're putting in will come out as cleaned material. Now the good thing is you have no water treatment. You get a dry mass that you can dispose of. And it's a very simple process. When it comes to rigid material or films that have a lot of paper stock labels, like distribution film, we've partnered up with another company that makes a dry cleaning process that creates a lot more friction And with that, we can actually remove all of the labels from the film and also clean up rigid materials, get the labels off bottles and containers. And that happens inside that machine through a this is the friction rotor inside that machine that creates a lot of force on the material, and we have a multi-edge screen basket around it. So it allows for a lot of friction, and it basically opens up the packages of stretch to single layers. It fluffs it up, so when it comes out, you're looking really at 1.5 pounds a cubic foot at the most. You can stuff your pillow with it. These are just a couple of examples. Even so, often the pyrolysis does not want PET, but this just is an example of what an input looks like and what a clean flake looks. So here on the left, you see the PET flake before the wash. This is aspirated material, so before we go into the actual friction wash, we use an aspiration system to get all the loose film and paper out. This is the material that comes out of the actual centrifuge. This is the fine paper that is rubbed off the surface, and any other contaminants like residual from sugar-based stuff like soda. And this is what on the bottom right is what the actual clean flake looks like. Same here. This is rigid flower pots. At the top, you can see the input, dirty flower pots that are shredded. The middle is actually what's being removed. The bottom is the clean flake. This is HDPE containers. You see the same thing. In this case, we didn't aspirate the material. It was just run through the friction washer because there was no loose paper in it. And so it basically fiberizes any type of paper and becomes a dry to medium dry mass that you can dispose of or could use as a fuel in the cement industry. And this is the last example of it. This is stretch film. On the left side, you see the shredded film with all the contaminants in it. There's paper packs, wood pieces, and rigid plastic in it. Through an aspiration process, we separate all of the rigids as well as the wood and metal pieces that still might be in it. And this is what the clean flake looked like. Almost too good to use it in pyrolysis. And then when it comes to the film, since it becomes fluffed up so badly through the process, again, a lot of people have to get a higher density out of it. So by utilizing a pellet mill, you can increase it from 1.5 pounds a cubic foot to about 18 to 20 pounds a cubic foot. This is what these pellets look like. So they have a good flowability, easy to mechanically convey. And yeah, that's about all I have to say today. So if you have any questions. None.
Hartmut, I know I will chime in because I had Hartmut, as I mentioned, do that trial for us, where we actually shredded, because we were running a trial for a cement plant. We're looking at mulch films. And the problem, he mentioned contamination rates of 30%, right? Well, in Florida, mulch films, now it's 70 to almost 80%. And so it's been really, really problematic to try to deal with that type of material. So Hartmut brought in one of his big shredders and a couple of, it wasn't a trommel screen, it was a shaker screen.
This screen.
this green, right? And so we were able, through our initial phase, to drop that 70+% soil contamination down to around 30%. We're still trying to do some more trials, and I want to bring him back in with some different equipment and run some linear more screens, whether it's that or air knives or whatever it is, to further separate out that soil, because it has some opportunities. All right, our next presenter, moving on, is Rebecca Brown. So Rebecca, all you, ma'am.
Great. Thank you guys all for, sticking around and on the Friday afternoon. So my name's Becca Brown. I'm a microbiologist at the Idaho National Lab. So for those of you that are, don't know much about the Idaho National Lab, we specialize in pre-processing of mostly, historically, it's been lignocellulosic feedstocks, so like corn stover. And in the last few years, we've kind of been transitioning into getting into more MSW. And so this is a picture of some of our team sampling and hand sorting some MSW. And when I became a microbiologist, I did not think that I would be an overpaid trash sorter, but here we are. So I don't need to tell you guys, the importance of MSW, and I don't need to define it for you. But to be recycled, MSW needs to be, at a certain level of cleanliness, and you just don't get that with most MSW. It's at a landfill or MRF residuals. And so we want to take this MSW and divert it away from the landfill and try to decontaminate it to get better yields, basically. So in our project goals were to understand the types of contamination present that are common in the streams that we're receiving, and to develop some decontamination methods to see if we can improve yields. And so, like I said earlier, we specialize in pre-processing, but we kind of have to dabble a little bit in conversion in order to assess how well our pre-processing works. So I'm going to kind of go into that a little bit. So this is a little shameless self-promotion. So we just published a paper in Frontiers in Energy Research this year. And that's the first part of my talk, is I'm just going to be giving a quick overview. For time, I'm not going to go into the details, but I'm happy to talk with anyone afterwards if you need more details. But check out this paper, because I need more citations. So this is just kind of an overview of how we did our process. So we received MSW paper plastic. So to be more specific, they were actually MRF residuals. And we coned and quartered them on a large tarp that had a quadrant on it, and basically sampled half of the material and reserved half. We then performed mass balance characterization, size reduction, decontamination, and then conversion screening. So because we had two different streams, we had mixed paper and mixed plastic, we used two different conversion methods to screen our performance. And so for the mixed paper, we were using a low temperature conversion, which is enzymatic hydrolysis. And then for the plastic stream, we're using microwave assisted pyrolysis. And so I won't really go too much into this, but we did a lot of characterization, hand sorting, and mass balance. And so the interesting thing that I do want to point out, so in the, the very bottom two pie charts, so the majority, the one on the right shows the kinds of plastics that we did receive. And the thing that I found interesting is that even though these are MRF residuals, we're getting the majority of the material is PET. So it is pretty contaminated. So it is, mechanically recyclable in theory, but it's still getting rejected from the MRF. Okay, so we quantified our contaminants. So the way that we did this was pretty rudimentary, really. We just kind of quantified the pieces of MSW that had specific kinds of common contaminants. So like food residue, ink, stickies, staples, things like that. And then we targeted the most common contaminants for decontamination. So the most common contaminants found in our mixed plastic stream was dirt and particulate. And so this could be a combination of actual dirt, residual container, like cleaning chemicals or food. It's just a combination of things that we were just calling dirt. And then as far as our paper stream, our most common contaminants were ink, plastic, and stickies. And so this has a lot of data on it. I'll just kind of give you the overview. But in our low temperature conversion tests for our mixed paper, we basically sorted out anything with ink, stickies, or any sort of plastic contamination. And we wanted to see how this would impact our enzymatic hydrolysis yields. And we found that those contaminants did not actually really impact them at all. But what did impact our yields is we used a dilute alkaline pretreatment and mechanical refining method, and found that by using this method that's commonly used for lignocellulosic biomass, that we were able to increase yields. So we are calling it a decontamination method, but it's something that would actually be done during conversion at like a biorefinery. And so another thing that we found interesting is that our copy paper samples, so we looked at the paper samples, the different fractions of paper. So what we noticed was that the copy paper during enzymatic hydrolysis had an increased level of fermentation inhibitors. So we're not really able to determine the impact of this with our experiments because we were just screening for sugar release. But at a further step down in the process, when we're doing fermentation, these inhibitors really could impact conversion. And so that's something we're looking into now in our further work. Another thing we noticed was that we had an increased increased pH during enzymatic hydrolysis. And so the enzymes that we're using have a very narrow range that they work in, between 5 and 5.55. And so if you look at this chart on the bottom here, so on the left we'll show newspaper, and so these are, our newspaper samples fall within that narrow pH range we need for our enzymes. But if you look over at the copy paper, they're really high pH. And so we think that this could really impact the yields that we're getting. So specifically, if you were bringing in a stream that had a high percentage of copy paper, this could really cause you problems if you're trying to do enzymatic hydrolysis and fermentation. So for our MSW plastic, kind of switching gears, so this was for our microwave-assisted pyrolysis experiments. So like I said earlier, our most common contaminant was this dirt and particulate that's present in the plastic. And so we took two different approaches. The first one was just a really simple, like detergent, and water, so like dish soap basically, and water, just washing away all of that dirt and particulate in there. And the other is using a solvent, so dimethyl ether, and someone talked about that earlier in some of these sessions. Thank you. And so we used DME to basically wash this, and the nice thing about this DME process is that you get a dry plastic afterwards, and you can recycle it. Like 98% of the DME can be recycled, so that's really interesting to us. And we found that in both the detergent and the solvent wash, we were able to increase our liquid oil yields. It wasn't without its problem, though, because our liquid oil products really quickly condensed into this white powder that's super difficult to separate from the char. And the char is very, very sticky, and it's just very difficult to work with and try to quantitate. And so this is something that we're working on troubleshooting now. So if anyone has any suggestions here, I know there's a lot of pyrolysis experts. We would be happy to hear what you have to say. And so the second part now is just focusing on some current work. So this is kind of follow-up work based on the results that we found in our paper that I was just talking about. So we want to use our data from our previous work to develop additional methods of decontamination, screen their conversion performance, and then further characterize the decontaminated samples and determine why there was or was not a yield increase. So the most important thing from this, I'll just kind of point out. So we screened a couple different wash processes. So we screened acid washing and alkaline washing, and then we also use DME as well for paper. But we did not really see much of an increase in yield except for in these three methods. So for copy paper, our acid wash was able to increase, 20% glucose increase, 33% xylose increase. And in cardboard, both acid wash and alkaline wash were able to increase our sugar yields. The interesting thing about the acid washing is that I told you before that, in our previous experiments, the copy paper had a really high pH. And so we think that, the phenomenon we're seeing here is basically we're just neutralizing that pH, the high pH that we see in copy paper. All right, so let's see. Our newspaper and copy paper blends were used to investigate the effect of pH. So we made basically blends of newspaper and copy paper and screened their conversion performance. And so interestingly, it appears that this pH, like we thought, did not have as big of an impact on yield. So as you can see, on the far left here, this mixture is 25% newspaper and 75% copy paper, and it had the highest yield at like 80%. But it also had the highest pH. So we're not really sure exactly what is causing this, and it's something we are actively going to be investigating in the future. Another interesting thing that we found is that with our newspaper and copy paper blends, our glucose and xylose yields could actually be predicted as the sum yields of their components, which is really interesting to us because, the streams that you might be getting from different MRFs or landfills could vary widely. And so it was really interesting to be able to say, we have this much percentage of copy paper, this much percentage of newspaper in our stream. Can we predict what our yields are going to be? And so one other thing we've done is we've done a little more investigating into why we have some of these increased yields with acid washing specifically. And so we did find that acid washing, according to these XRF results, removed alkaline earth metals. And that's shown here with the bars going into the negative. And we also enriched in cellulose, which is shown on the far right here. So basically we're, getting rid of a mass of these alkaline earth metals and enriching our concentration of cellulose. And this is in agreement with some previous results that we've seen where we've done grass clipping and paper blends, and we've done an acid wash with them as well. And it's in agreement with those results that we're decreasing our amount of alkaline earth metals. So in conclusion, our previous work, ink stickies, plastic contamination, and paper streams do not impact sugar yields in low temperature conversion. Dilute alkaline pretreatment and mechanical refining does increase sugar yield during low temperature conversion. Detergent and DME washing increases yield in high temperature conversion. And then our current work is that various washing methods can increase yields during low temperature conversion without a harsh pretreatment. And what I mean by that is so in pretreatment you usually have a chemical and then heat and then time incubation. So in these experiments it was just one of those, so just an acid wash. So we were able to get good yields without having that heat input and without having a long time incubation time. And then another interesting thing, obviously, high pH of copy paper does not seem to have a major impact on yield during low temperature conversion. And so our future directions are to further characterize these samples before and after decontamination, screen new methods, carry out decontamination on whole paper, so rather than just doing different fractions of the paper, we want to use the combined whole sample. Investigate the impact of pH and percent solids loading, so that seems to be something that we have noticed happening, is we tend to do our enzymatic hydrolysis at a low solids loading, but the industry really wants to have a high solids loading. And so how does the solids loading impact that pH and our yields? And then also our next step for pyrolysis is to troubleshoot our microwave pyrolysis and to be able to get better, more reliable results. And so obviously I want to thank all of our teams, so especially our principal investigator, Vicki Thompson, who was actually going to do this presentation originally. And go check out our paper, everybody. And here's my contact information, and I will take any questions you guys have.
I've got one for you right off the bat.
Okay.
On the DME, how did you all deal, now that was just a lab scale, your research, but does the DME cause any problems from a waste effluent aspect? If you're going to treat something to try to decontaminate it, do you not have a solvent that you've got to deal with?
So we like 98% of it can be recycled. We do have at the end of the cleaning process like an extract that has, you know, dirt and all that stuff in it. So that would definitely be the extract that we get out of this cleaned plastic would be our effluent that we would have to deal with, for sure. Yeah.
Preston, thank you.
So and what things do you need to troubleshoot in your microwave pyrolysis?
Yeah, so the instrument that we have, so the pyrolysis instrument has a long quartz tube that you will load into the instrument. And so we are trying to fabricate just like a little boat, basically, that you could put in there so that you could capture your char in the boat, and then all your volatiles will be condensed in the tube, so you'd be able to basically separate them. So that's our idea right now. We'll see if it works, but.
Any others? All right, thank you, Becca.
Thank you, guys.
And last but not least, thank you, Dr. Saha, for being our last presenter, and we'll turn it over to you, sir.
Good morning, everyone. I'm glad that still you guys have here. Like, when I saw the agenda and saw I'm the last presenter, I thought I had to present in front of no one. So thank you for being here. My presentation will be preprocessing on municipal solid waste towards thermal insulating material. So last couple of days, actually, the presentation I saw, like, you guys are talking about like TRL level 8 or 9. But as a national lab, as Becca said, like, her presentation as well, my presentation is kind of like TRL level 2, 3, or even maximum 4. So this presentation, like, I'll talk about like MSW. I think you already know about the MSW, but I'm lucky that I'm presenting last, so I'm gonna remind you again, like, what is MSW, how we are destroying our environment, the earth. And I'll talk about like the case studies we are doing with the MSW and our findings as of now and the future direction. So as we know, like, MSW is kind of garbage, like what we throw every day. So if you think about, like, if I throw a water bottle after using, what will happen? It's just a single bottle. But if you consider like the number of population we have in the United States, if everyone throw a bottle, how big that pile will be. So if you see the generation direction, like how that MSW is increasing towards like over the year, you can see like as per EPA in 2018, we generated about 293 million tons of MSW in the United States, which is about 94% higher than 1980. Now you can think about, like, okay, our population also increased from 1980 to 2018. Yes, you are right. But in that case, if you see like per capita generation, even that number is also increased about 34%, and which is about that number is also like higher than the other countries in the Europe. Like if you consider the Germany or UK, you see their generation is about 3.7 pound or 2.7 pound per person, where we are about 4.9 pounds per person. And when we are generating that MSW is like mostly like about, you can see like 23% is paper and cardboard, and you can see food waste is also like 22%. Now, we all are talking about how we can manage this MSW. In the left figure, you can see like that's the traditional like how we can manage this municipal solid waste. The best way, obviously, if we can cut the source. And the following is recycling, get the energy from it, and the easiest way to send it to the landfill. In the right figure, you can see that like that landfill, obviously the biggest one, but good thing about like over the time, over the year, the recycling is getting interesting. So it's getting it's taking a significant portion of that MSW and recycling it. So based on that management method, United States actually divided into 10 different regions. And obviously on those 10 regions, you can see landfill is the maximum one. But But if you see the different side, for example, East Coast, you will see like energy, like waste to energy is significant. But if you see the west side, you can see the compost or recycling is significant. So when we are recycling, you can see we are recycling about like 66% of the paper and cardboard. When we are composting mainly the agricultural, like air trimming or food waste. But when we are sending to landfill or waste to energy, we are actually utilizing all of these things. So if you see the summary, like after doing this type of like management, what benefits we are getting from in terms of greenhouse gas. So this is the 2018 data, where out of the 293 million tons, we recycle about like 69 compost to like 25 million tons, and waste to energy is about 35 million tons. And where we get those positive like credit, but when you send it like 146 to the landfill, we are getting like kind of negative impact. Even combining with that, we are getting about 194 million tons of CO2 equivalent credit, which is about like 42 million passenger car emission throughout the year. So think about it, after sending 50% of that material to the landfill, still we are getting some sort of benefit. But if we could utilize the landfill portion a little more, then we can get more benefit. So when we are sending that landfill, like 146 to landfill, you can see like more than 15% of the methane emission is coming from that landfill. And which is you can see like equivalent to like the emission from 20 million tons of passenger cars. And those methane actually can absorb like 20 times higher solar radiation, which is ultimately global warming. So as I mentioned earlier, when we are sending to the landfill, we are sending everything. Now the question is, what are the potentials, what we can do from here? What are the potentials of this MSW? You all talk about like we can do different things. We can do gasification, we can make syngas, liquid product, or gaseous, like solid product as well. So most of the processes, like they have some sort of limitation. Like we don't, for example, when we're talking about gasification, we think about, okay, we cannot send the PVC. We want to minimize the inorganics into it. So the way we were thinking in our case studies, we thought like, okay, how we can utilize all of the MSW without like ignoring anything. So we went to a solid production route, and in this presentation specifically, I will talk about like the insulation material. So the sample we used in our process, like we used reject from the MRF, so which is directly going through the landfill. We just read out that truck, and we said, okay, dump into our facility. So we used that material, as well as we tested some paper fraction as plastic fraction as well to see like how that thing work and the combination of those. And we used commercial cellulose as our baseline to see where we are compared to cellulose insulation. So the way we did the initial pre-processing is like we, as I said, this is the actually material we received from the MRF facility, the reject. only one thing we just get rid of from the pile is the metal. Because of the limitation of our shredding instrument, we wanted to remove the metal from that. And after processing, we actually got two different feedstock. As I said, this is a broad study. We wanted to see different perspective, different product. So we separated into fines and dirt as a you can see on the bottom, and this is we call as an on-spec material. So that on-spec material we tested for the insulation as well as the fines. We are actually doing something else, we are using as a potential for the cementous material for the asphalt. So these are the nomenclature you will see in the next part of the presentation. We use as I said, mixed paper, mixed plastic, MSW with different sizes, and we mix them to see how they affect. So before we doing the thermal properties, we wanted to see some physical properties of the material. Although we said paper 13 millimeter or plastic 13 millimeter, we processed through same process, but their size distribution was different. Because they were different in for example, those plastic we are working with, they were kind of elastic. So when we shred it, it actually squeeze and pass through the screen instead of cut and make the small pieces like paper. So you can see that even though we are talking about mixed plastic 13 millimeter, you can see that their distribution is different than mixed paper 13 millimeter. So here D10, D50, or D90 is representing, for example, for D10 is representing the opening required to pass 10% of the material. So another properties we check the density, which is very important for the insulating material, because it will give you some sort of idea what will be the void space inside the material when you will pack them. So we tested the bulk density, and we saw that the bulk density of the material is actually different, and it's actually varied with the size. So when we are reducing the size, we are increasing the bulk density, which makes sense because when we are reducing the size, we can actually pack better. So we can minimize that void space between one particle to another particle. We checked the skeletal density of the material, and we saw that skeletal density also changes with different material as well as size of the each material. Similar thing happened to the envelope density as well. When we check that envelope density and skeletal density and see the porosity of the material, we saw that cellulose has about 95% porosity, where our MSW and MSW also has higher porosity, is about 85-ish percentage. That means we had some sort of feelings we might get similar behavior of the insulating properties of the municipal solid waste compared to the cellulose. So as we want to use our material as an insulating material, and definitely we don't want to, for example, if we put it into the wall, we don't want to change that material every year. So we wanted to see how that material actually compress over the time. So we did the compressibility of the material. This test is very short test, so we did it only for 1 hour to see whether we can see any change on that compressibility or not. We can see from here that cellulose has the more compressibility behavior, because we saw the cellulose has the more porous structure. So when you press it, it just squeezes it. And we saw the paper has the least compressive effect. So as we saw that paper has the minimum porosity as well. So finally, we tested our material in terms of thermal properties. So we use a transient plane source method where we actually packed our material with a certain packing density. And we we put the sample on a heat source, and we pass the current through a known resistor, and we measure the temperature difference of the material. When we record the temperature difference, we actually feed the equation to get the thermal conductivity. So as soon as we know the thermal conductivity, we calculated the diffusivity as well as R value, which is commercially like well-known number for the cellulose for the insulating material. When we see like this figure is actually telling like how the packing density of each material is actually affecting on the thermal properties. You can see with the increase of the packing density, we are increasing the thermal conductivity, which is making sense because when you're compressing like packing density, when we are increasing the packing density means we are like the particle is coming close together. So when they are in contact, they can actually transfer heat better. That means it works as a more conductive material. When we are increasing the conductivity, that means obviously we will see it will oppositely affect on the diffusivity as well as R value, as those are inversely proportional. This figure is telling about like the effect of the particle size. So you can see like for a specific packing density, if we reduce the particle size, we saw the increase of the R value. This is because like when we are making that smaller particle, and we saw in the porosity, so we are getting more porous structure when we are reducing the size. So when we have more porous structure, we have like more air trap into it. That means we are reducing the heat transfer. So that we got that R value higher, means like less conductivity. So when we tested like to see like whether the different fraction of the paper or plastic they have effect or not, we saw like it depends on like the its fraction type. For example, we saw that the glossy paper they had like less R value, that actually reminding us like most likely that glossy paper it has like higher conductivity than other paper. That's why we saw that less R value on that paper. But in plastic, we didn't see that much of change in the R value with the different type of plastic. So when we mix them together in different ratio, we wanted to see like, for example, when we do the conversion side, we see like sometimes if you mix A and B, you might get some sort of like synergistic effect on the product. We wanted to see whether if we mix those paper and plastic, whether it changes our thermal properties or not. But we didn't see that much of change in the thermal properties, like especially the R value. We didn't see that much of change because previously we saw that like even mixed plastic or mixed paper, they have the R value is kind of similar. So they behave like in the way we mixed it. So in conclusion, I would like to say like that's the result we found like the R value of the cellulose we measured about 3.35-ish, and the other MSW and plastic and paper fraction, all of them are within the 70% band. So that means like we are getting something not better than cellulose definitely, but most likely it could be compatible with the cellulose. And we saw that they are highly dependent on the porosity of the structure and how we are packing the material. And this is just the beginning. So although our results are encouraging, but we are not there yet to use this material for the home building or insulating material, because like when you want to use that as a insulating material in your home, you want to make sure like they are fire redundant or like what they are emitting over the time. So we need to test that, as well as like, MSW is contaminated, so we don't want to put some contaminant in our home. So we want to like add some sort of like antifungal chemicals that can minimize the like the growing of the insect or molding. So one of the things is usually use the boric acid, so which is kind of a fine particles. So as I claim that like we are with the fine like smaller size material, we are making the higher porosity, so we will get better thermal properties. But if we use this fine boric acid, that pore might clog. So we don't know how that will behave after adding those boric acid. So that's the thing we want to test as well. And some of the tests I said like we did it for a short time, which is like good for initial screening, but it's not good for long term. As we are gonna use insulation for a few years, definitely to do some experiment in few years is not that feasible, but definitely we want to do something for a week or a month to see how that performance behave. By this, I would like to acknowledge my colleagues, Lionel, who helped me on some of the experiment, and finally the funding agency. By this, thank you, everyone. If you have any question, I would like to answer.
Any questions for Nepu? All right, with that. Yes, sir. Grab that so we can get it recorded.
This might be just an issue with terms, but was the testing was against fiber cellulose insulation? Did you also do testing with fiberglass?
No.
Or against fiberglass insulation?
We only tested like we only tested cellulose as our baseline. So we test cellulose and compared that cellulose with our feedstock. The feedstock I just talked about like plastic, paper, and MSW as it is.
All right. Let me just make a couple of final comments. First off, a thank you to our AV team. So Tim and Derek, thank you, gentlemen, for continuing this on. When I used to run these conferences years ago, I did it all myself. AV, moderate, everything. I just can't do that anymore. So I just thank you, gentlemen, for being here for us. In conclusion, I will make sure that everybody gets the proceedings. I'll try to get it done over the weekend. Give me a little bit to compile everything. We've got to tweak some of the videos just a little bit, and then we've got to shoot all the presentations to PDF. I'll compile that out and get it out to you, so check your emails probably Monday. And also check your spam folders, because I know when I send out my emails with my BBC email, they're going into spam folders, especially when I send my YouTube link. It has a problem, so make sure if you don't see it by Monday or Tuesday, check your spam folders. All right, any other questions before we conclude? All right, with that, thank you. We'll be back doing this event in April in Atlanta with SWANA and SOAR. And then I've had conversations with several of you here in the room, and for some of you that already left, I think we're going to try to come back here in 2024 and redo the conference here. And I'll probably bring back agricultural plastic and do it at the same time. So we'll do them back to back. Kevin, I see your thumbs up. So, all right. Well, thank you, everybody. Have a safe trip home.